All right. Hi, everybody. So thanks for coming. Um, I'm Sergei. So I'll give introductory lectures in BPS states and quantum invariants. So there are kind of two keywords. So intro into BPS counting and quantum invariants. So there are two basic keywords here. So BPS counting refers to counting something. And one thing we like about this sort of counting, even if you don't know what B, P, and S stand for, is that these are certain integer counts. So this part of the story will have to do with integrality in a crucial way. So integrality, and I think I should probably draw here a happy face because all integrality properties in mathematics are usually good and interesting and so on. And another keyword is quantum, so this may refer to two different things. If you're a physicist, this is same quantum as in quantum physics, quantum mechanics, quantum field theory, so there is going to be some kind of H bar. But then also we'll see versions of quantum as in quantum groups, such as UQ of SL2. Most of the time, I'll work with just simplest possible underlying Lie algebra, which will be SL2 in my case. Or, so this is subject of quantum groups. That's actually what I meant when I gave the title, and I don't remember if I had the abstract, but if I did, that's what it's going to be. But then there is another version of quantum as in quantum algebra. And this usually refers to some infinite dimensional or large algebra, which is non-commutative deformation of, say, algebra functions or something like that. And vertex algebras, chiral algebras fall into this general field of quantum algebra, and we'll see connections to vertex algebras. In fact, one of my goals is to make a very solid connection to logarithmic vertex algebras that Terry is talking about. So we'll see a lot of relations there. So this is decoding the title, but in practice, we'll talk about several ingredients. So in this first introductory lecture, I'll outline the map of where we're heading, and then the rest of the lectures will be to build on that, flesh things out, and so on. And there will be three basic ingredients. So first ingredient is two-dimensional 0,2 theories so I'll write a long version and then I'll give you shorter ones, from compactification of 6D 0,2 5-brane theory on 4 manifolds. On, maybe I should say, emphasize that on smooth 4-dimensional manifolds. So that's going to be ingredient number one. Ingredient number two will be 3-dimensional n equals 2 theories that arise in a similar way by compactifying 6-dimensional 0,2 theory on 3 manifolds. And just as aside, so that's why I'm going to use a separate board. You don't have to, if you're taking notes, you don't necessarily have to write what's going to be here. I'll probably try to erase it soon. I want to say that there is a word here, compactification. And this is the same word that string theorists use to compactify string theory on Calabi-Yaos and so on. So as a remark, this can be viewed as a baby version or toy version of string compactifications, which means that you start your life in 10 dimensions or 11 dimensions, and you try to find some either 6-dimensional or 7-dimensional manifold with the right properties or background such that you end up in a 4-dimensional world where we live. So this is me. And what we're going to be discussing is, so that's why I call it a baby version or toy version, analogous procedure where you start in 6 dimensions, and by finding a suitable, let's say, 3-manifold, I'm going to call it M3. So along the way, let's introduce some notations. 4 manifolds will be M4, 3 manifolds will be M3. You can produce physics in, for example, 3 dimensions. And if I replace this 3 by 4, then simple counting tells me that 6 minus 4 is 2, so we end up with a 2-dimensional theory. And though there I specify even precise amounts of supersymmetry and so on. So this is obviously smaller in the sense that 6 dimensions is less than 10 dimensions or 11 dimensions. And physics here is much easier, but it captures some interesting aspects. For instance, string theory, the main feature of string theory is that it's quite non-local. So unlike local QFT, so it has winding modes and stringing excitations, so it has a scale. So it's not a local theory. And the same is true about this theory. So although it's non-local in a minimal way, so it's interesting from QFT perspective. So that's where this starts. So in that sense, it's a baby version of what string theorists like to do. So we can, on the one hand, borrow some of the lessons, and we'll talk about some simple exercises where we'll use compactification in exactly the same way as Kaluza and Klein used more than 100 years ago. So we will be doing very old stuff. But also, some of the delicate properties that we'll be discussing can serve as a very good lesson for compactification of string theory if we upgrade this process from 6 dimensions to wherever string theorists want to live. Okay. I'm not going to assume any knowledge of string theory. That's why this was just an aside. And as promised, I'll erase it. Okay. So then, in addition, and this will be important part of the what our discussion, we'll talk about combination of these two systems. So this will be 2D, 3D combined systems. So basically, it involves 3D. So to decode it, it's will be a choice of 3D n equals 2 theory plus 2-dimensional 0-2 boundary condition. And you can think of this in the following pictorial way. I'll draw these pictures in many different ways. So for instance, here I'm trying to illustrate a half space such that in this part of the bulk, you have 3D n equals 2 physics. And here on the boundary, you have a 2-dimensional 0-2 physics, some particular boundary condition. It's in itself is BPS. In fact, it's half BPS. So this is particular half BPS boundary condition. because it preserves exactly half of the supersymmetry of three-dimensional bulk. But this is not what the word BPS in the title refers to. That word refers to further counting some nice, so for non-physicists, for mathematicians, the word BPS can just stand for nice states in this fairly complicated physical system. So the system was first introduced in our joint work with Abhijit Gada and Pavel Putrov in 2013. And besides acknowledging my collaborators, which of course is something I should do, I want to refer you to this paper, Walls, Lines, etc., where some of the basic ingredients of what I'll be talking about come from. And in some sense, these lectures will be based on fairly old developments. My main focus will be on more than 10 years old, so on developments around that year. But because it's an introductory course, I'll try to also sort of show you how this developments now led to many future applications. Future means more recent, and how this is used. In particular, in this context, so we'll talk about this three different systems, either 2D, 3D, or their combined thing. And then in this context, it already starts looking pretty complicated. We'll talk about BPS spectra. In fact, in all of the cases, in all three, it makes sense to ask about BPS spectra. So if I ask you, what is a spectrum? Mathematically, there are several kind of in homotopy theory, there is one notion and so on. But for physicists, or if you're simple-minded high school students, spectrum means spectrum of states. So therefore, without saying it, most of the time, I and probably others just mean spectra of states. And this is not so, even though this is still looks pretty serious, very advanced, something that could be title of the paper, it's actually something very simple that you all know about, and there are simple ways to think about it. So let's consider an example, just good old friend harmonic oscillator, okay? You all know what the spectrum is in this case. It's not rocket science. You know that you have energy states, so that's what I'm trying to illustrate here. E sub n for every non-negative integer, or non-negative integer n, you have E sub n, which is something like h bar n plus a half. Okay. So that's nice picture of a spectrum. There is, hopefully it's very familiar. There is nothing terribly mysterious. But then very convenient way to think about the spectrum is to produce a partition function or generating series. So you can basically sum over all possible states in your system. Here it happens that n naturally identifies itself with an integer, but imagine that you have a very complex system, such as, I don't know, quantum something, phase transition. So then you can still sum over all states. So here I'll write sum over all states, or maybe all nice states, if that applies. For us, nice will be BPS. And write q to the en, okay? Or just write exponential of energy with, so maybe that's even more natural, I don't know, with another parameter, something like mu. Already at this stage, you see that it's sort of convenient to use, when I write q, it's convenient sometimes to identify q with exponential of h bar, and that's kind of here coincidence, but this is something we're gonna use later on in various other contexts. But in any case, for harmonic oscillator, since I'm still in this example territory, I can exactly write what that is because it's gonna be q to the 1/2, 1 plus q squared plus dot 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 and so on, right? So this is a very simple Q series, and everything, I promise you, so here I put lots of physicsy words and so on, but everything I'm gonna talk about in the remaining lectures, every single statement can be encoded in form of this simple, or not this particular, but a simple Q series like that. Because this is, for all intents purposes, encodes what we want to know about our quantum system. It tells us how many states are there at a given level, in this case, energy level. So in particular, there are analogs of this. So talking about discounting, in particular for our applications, in our case, there will be such a series naturally associated to 2D02 theory. So it has a special name. It's called elliptic genus. So this is something that may have more complicated definitions, applications, but basically it is exactly the same as counting states of a harmonic oscillator, except that we apply it to 1 + 1 dimensional quantum field theory. Yes. Is this? I don't know what this word means. I'm trying to decode it to, as I'm not going to talk about loop spaces, Dirac operator at all, but possibly it means, yeah, so it depends how energy is defined. So in fact, the energy here is going to be very loose in this interpretation. So energy in harmonic oscillator was literally energy of state. So here in 2 dimensions, yeah, maybe I should sort of draw a picture. Important thing about 2-dimensional world. So in 2D, which is sometimes written as 1 + 1, we have massless objects being at fermions, bosons. They run with the speed of light, and they basically have nowhere to run. So if this is my time direction, maybe I should use different color. So let me try to draw coordinate system. So this is time, this is 1-dimensional space, and 1 + 1 dimensional world is literally like a blackboard. So it is what I'm drawing. And if I have waves running with the speed of light, then they have only 2 options to run to the left and to the right. In other words, I don't have more spatial dimensions to really rotate things. My rotation is unfortunately limited to only this binary choice, left to right. And since we're talking about, so I'll take advantage of Lotta's question to introduce a couple of more notations. In this context, we usually call left chiral. This is the same as holomorphic. In this particular context, these 2 terms are completely identical. So chiral and holomorphic may also mean other things in 6 dimensions, but here they're totally identical. And usually conventions are such that everything moving to the right is, well, non-holomorphic. It's also chiral, but with right chirality, as we will say. And sometimes I'll just abbreviate this as left and right, or people use sometimes bars to indicate the difference. In particular, getting finally a little closer to Lotta's question, there are 2 Hamiltonians, or 2 notions of energy here in this context. One is denoted by L0, and I hope you've seen this in Terry's lectures. And the other is denoted by L0 bar, that's right-moving energy or energy of right-moving excitations. And this elliptic genus, which is what I'm trying to define, it's basically the same thing. It's essentially trace over our states in a system. So I'll just write states because this is introduction and kind of supposed to be simple, of Q to the L naught. So in other words, we organize the spectrum. So again, nice states, or I'll just say left states for now. We organize the spectrum with respect to some energy, and in elliptic genus, the role of energy is this kind of diagonal left-moving energy. So yes, so that's why I decided to write left states. I can also say that this is either super trace, or people also write trace of all states, and then stick here a -1 to the right-moving fermion number, so Fr. Q to the L naught part is going to be the same. So this way of writing is more complicated. So to emphasize the important thing that we're counting energy of left-moving part of the spectrum in nice subspace, I decided to write this. So and that's still correct, but captures exactly what we care about. So the notion of energy, to go back to Lotta's question, will be very different and sometimes will be skewed, no pun intended. So it is kind of tilted here on the picture. And but I promise you that in all cases, when we're, so the point was to, again, bring it to a kind of simpler context to say that at every point in our discussion, there will be always a way to express whatever we care about as a Q-series. An important thing, it will have a lot to do, or similarities, with this simple example of harmonic oscillator. It will start as a fractional power of Q. So this 1/2 hopefully is not a mystery to you. So this is basically ground state energy. Ground state energy. And there will be exactly the same structure, and the rest is integer powers, integer coefficient. So that's the integrality I was talking about, because we have integer number of states per every level. We may have super complicated systems, but number of states is still going to be integer. So that's exactly that integrality that will be crucial for us. And everything we're going to talk about will have the same structure. It will be Q to some fractional power out front, and then integer powers, integer coefficients, even in the super other advanced complicated systems. So in particular, I don't know if Terry showed you characters of VOAs. He nods, so probably he did. I don't know if he said that in that context, this is conformal or scaling dimension. Not quite, okay. So it has slightly different name in context of two-dimensional CFTs or VOAs, but the meaning is still the same. Meaning is still that it's ground state energy. So if you're ever lost, if I show you some super complicated Q-series expansion, I'm a mathematician, so to me, I'll be talking about Q-series arising in various different ways. Think about this analogy. Think about the simplest harmonic oscillator, and that's what we're doing. It's a recording device for states of a maybe glorified harmonic oscillator. In fact, here I like to quote one of my favorite physicists, Sidney Coleman. So he said that life of a theoretical physicist is studying harmonic oscillator in ever-increasing levels of details. So whatever we're going to be doing with all these fancy words is just going to be a fancier version of harmonic oscillator. That's all there is. Okay. So any other questions? So I'm trying to set up the stage. So for me, the physics part is going to be this. The mathematical outcome and where we spend mathematical time will be a Q-series. And that's what I mean by the BPS spectrum state counting. So I may not get into this in the lectures, unlike, possibly in the very last lecture. But here I want to make a comment that I assumed that the starting point is 6-dimensional 0-2 fibrine theory. And the good thing about theories is that they're sort of unique. Um, I'll comment on this in a second, in the sense that they're labeled by very structured structure, namely Cartan types of type A, D, or E. So if you take brains, then you typically end up with either UN or SUN theories of Cartan type A, and therefore you can just specify capital N. Notice that it's slightly different from the way I'm writing curly N. This is supersymmetry. This is number of fibranes. And for me, N is going to be 2 most of the time. I'll try to do just like low rank or something extremely simple. But we could have, as a starting point, something else. We could have started in the world of 6-dimensional 0-1 theories. Okay, that's not a great color. Let's see if this will be better. Yes. So suppose we start with 0-1. So then we have a lot more choices. And there are many more 0-1 theories than 0-2 theories for actually obvious reason, because this requires less constraints, less structure. So there are more random things in the world. So with less structure, you can find more. So if you use this as a starting point, a lot of things go through. In fact, you can basically play like a children's game. So a 3-year-old can probably spot 0-2s appearing in different places. So if you replace all 0-2s by 0-1s, everything is still going to be correct. So you can take your 0-1 6-dimensional theories, whatever many of them they are, compactify them on 4-manifold, you're going to find 0-1 2-dimensional theories. If you do the same for 3-manifolds, everything basically goes by half in terms of supersymmetry. Okay, so this will be n equals 1, this will be 0-1, and so on and so forth. Okay. So you can still say all of that. The only interesting question is that, in fact, in that context, you have, you still have elliptic genus and its generalization to this 3-dimensional combined systems and so on, that I'll tell you more about. But it's actually hard to compute. It's hard to compute because I'll come to this point in a second. Many of these theories are extremely strongly coupled. And we have to know something about their dynamics or constraints from supersymmetry to bootstrap it. And 0-1 supersymmetry in 2 dimensions is almost like no supersymmetry. It's actually no help at all, or almost no help, because it has only one real supercharge, and that's tiny. I mean, string theory, just for comparison, has 32. That's like order of magnitude and factor of 3 higher. So that's a lot. But 0-1 and 2 dimensions is pretty much nothing. So that's why people here, when they study such theories, they focus on very basic properties, such as anomalies. And this is something computable. This is something you can study. An analog of this 2D, 3D combined world will naturally land you in a world of TMF. So I don't have space to decode this, but this stands for topological modular forms. So those of you who love topology and modular forms, this is something we may come back to in, if we have time. Okay. So throughout this lectures, I'll give you homework assignments. These are homeworks that are instructive and relatively easy to do, and I encourage you to do it so you have actually get more out of these lectures. And I'll also outline problems for actual research. So problems to which I don't know solutions, and problems that if you actually solve, it's probably worth writing a paper or maybe a series of papers. So therefore, I'm going to distinguish. I'll try to be careful about my language. When I say homework, I mean homework. When I say problem, I mean it's not anybody's problem. There is nothing wrong with any of what I'm saying. It's just a problem for research. So therefore, here I actually have good opportunity to tell you about first research problem, which is the following. So this story about TMF, again, if we have time, we'll talk about it in more detail. If not, then that's good enough for now. We'll be studying a space of theories, which is actually interesting and good, but also requires lots of qualifications, because as a mathematician, when I see such a thing, I would say, I have no idea what we mean by this. And even if I try to put a physicist hat, I would still have hard trouble understanding it. But in any case, whatever it is, take your favorite picture of some infinite dimensional space of coupling constants, terminal Lagrangian, that you can add to the theory, deform it, and so on and so forth. So modular deformations. Again, I don't know, maybe I should put this in quotes. Think about deformations such as RG flows, relevant, irrelevant operators, everything basically you can throw in there. Again, decoding what this quotient means is a separate lecture. But usually when people talk about TMF and connection physics, this sort of picture is arising or under kind of in the background. And my first, so in the case of 0-1 theories, it's actually well understood, and there is a mathematical meaning and definition to this. So if I have time to say generalizations to 0-1, I'll come back to this and give you proper mathematical meaning of it. But one problem that I don't know the answer to, or after spending some time with topological modular forms that I realize is actually a good problem, is work out. By work out, I mean give mathematical meaning or give mathematical definition, what one can call 0-2 version of TMF. So there should be an analog of mathematically well-defined theory of topological modular forms that classifies 0-2 theories, namely what we were talking a moment ago, theories, two-dimensional theories with 0-2 rather than 0-1 supersymmetry, modular these deformations. So I want to point out that, of course, it's true that space of 0-2 theories, whatever it is, again, we don't know, but I mean, we can discuss it, but whatever it is, it's clearly a subspace of space of 0-1 theories, simply because we're requiring additional structure. And it's a strictly subspace because it's easy to find candidates that are 0-1 theories which are not 0-2, so it's not equal. So therefore, you could say, well, if I already have mathematical definition for 0-1, why is not my answer going to be subspace of whatever it is for 0-2? And the reason is that there is also denominator. So we have, if we proceed from 0-1, where this quotient is exactly mathematically well-defined TMF, we're actually changing both numerator and denominator. And it's not obvious, at least to me, how the quotient is going to change. So it's not clear that this 0-2 version, for example, will be contained in what we usually call topological modular forms. It is just a different thing. So therefore, it's a good problem. It's a good research problem of the type that if you solve, it probably will take more than one paper, in fact. So I think it's going to be, it's a kind of massive project. Yeah. No, even that. So that's the starting point. So that's another, so thank you for asking, and it gives me opportunity to point out that there are other notions of spectra aside from what I'm talking about. So that's the spectrum in the context of homotopy theory. Yeah. So, and it's, yeah, it's a important question to realize this program in this case. It's basically, that's what the problem is, but we don't know. Yeah. Okay. So other questions, comments? So before I erase, so this is kind of first set of blackboards covering where we're heading, basic ingredients, basic players. I'll try to stay within this soccer team box, not get too far out. Um, but yeah, so that's why I wanted to pause, ask for questions. Maybe I'll ask you a question. Since I don't know what the background is, when I say 0-2 theory in 2 dimensions, how many of you feel comfortable with that? Okay, good show of hands, yeah. Well, when I say quantum group or quantum algebra, how many of you feel comfortable with that? Okay, good. I hope it's not the same set of people. I didn't count. If it is, it's actually fantastic. All right, so far so good. If I mean, this is supposed to be introductory, so therefore I'm optimizing, in a sense of computer science, 2 goals. One goal is to be pedagogical, so I don't want to go too fast. I don't want to lose any of you. So if there are questions, even at this stage, maybe I started too high, ask. I mean, I should be able to answer if I know the answer. My second goal is to give you introduction to something reasonably modern, reasonably current. So that's why I need your help in this optimization problem in general. Okay, maybe I'll keep the boards for a second. It's actually going to be useful to me. So this was, in some sense, answer to a question, what? What are we going to be studying? What is our playing field? So I promise, if this sounds scary, we'll spend some time, you'll get familiarity with the systems, but we won't get too far out. So I basically charted all the outer boundaries of where we can be. Now, important question is why, okay? So very often we venture into directions just because our advisor told us so, but I think, and I always tell, especially my students, that it's a good idea to ask yourself why we're doing this. And I want to tell you a story that in business it's called Toyota method. So Toyota is a founder of Toyota Corporation, so automaker. And he was a great leader, and every time there was a problem, he would come and ask a question, why? But the reason it's called Toyota method, and you can Google it, it's a real term, I mean, I didn't make it up, is he would ask the question, why 5 times? So he iterated. So for instance, there was an accident on a production floor. So he would ask why. They said, oh, somebody got hurt on a conveyor belt. I mean, somebody's arm got chopped. I don't know, something like that. So he would ask, why did that happen? Well, it turns out that the person had his lunchbox and so on somewhere on a conveyor belt, and maybe it was during lunchtime, I don't know. So then he would ask, why did that happen? Why lunchbox was not in the right place? And for example, it turns out that there are no tables or there is no infrastructure for a proper lunch in that space. So asking question why 5 times gets you to the gist of things, gets you to understand why in a kind of real big picture you're doing this or what you're doing. So same thing here. Whatever I tell you, it's a good idea to ask why we're doing this, or what's the benefit. I mean, be a little bit more strategic because your time is extremely precious. And if you're sitting here and learning something, same applies to every subject, it's good to know what is the end goal. I mean, like benefit ratio, cost benefit ratio, things like that. So therefore, I already told you what, and we'll dive into details, but it's important for me to emphasize why we're doing this. So what's the benefit and what we're going to gain by this? One obvious answer, which is way too obvious, especially in considerations of Mr. Toyota, is that, well, we can produce new invariants of 3 manifolds and 4 manifolds. Of 3 manifolds, I'm going to call M3 and 4 manifolds. I'm going to call them M4. Okay. Honestly, this is my personal motivation. So when I came to the subject, and I'm still somewhat in the subject, my interest was just to understand new invariants of 3 manifolds and 4 manifolds. So, and that's what I'll fulfill during this lecture, is we'll see some new invariants of 3 manifolds and 4 manifolds arising from this structure. Sometimes, because say 3D theory is coming from 3 manifolds, this is called 3D correspondence. That's yet another name for what we're gonna talk about, from 3D correspondence. And many things I'm describing have also some dual names. For instance, this combined 2D, 3D index is often called either half index or chiral something. And again, there are lots of different names. But actually, what's cool about it, and the reason I decided to use this as a subject for the lectures, is that there are multiple benefits. So string theory is often positioned string theory as a theory that, well, didn't solve maybe its original intended purpose of unifying forces in nature, but it did solve problems from other fields that it wasn't expected to solve, such as problems related to information paradox, black hole microstates, and other things, right? So here, this is a baby version of string theory compactification that I mentioned in the beginning, and there is a baby version of solving problems from other fields. For instance, when I started working on this, I had no idea that studying the subject will give us new perspective. So it offers also new perspectives on quantum groups and quantum algebras, in particular, logarithmic vertex operator algebras. Okay. So in context of quantum groups, just to kind of give you a little appetizer, usually quantum groups are extremely abstract. So they're not even groups in strict mathematical sense. They're formulated using generators and relations and so on and so forth, which is like a table of rules, traffic rules. But originally, the subject is extremely algebraic, which is fine because people who invented it are extremely algebraic, such as George Lustig, for example. But what this perspective gives you, that's also very common for string theory, so it shouldn't be a big surprise, it gives you geometric interpretation of many things that you see. For instance, the parameter q that I introduced somewhere on the board already, for example, uq was using parameter q, and somewhere I had that it's exponential of h bar. So that fellow is going to be, for us, geometric parameter very similar to Nekrasov's omega background and some fugacity for rotation and so on. So therefore, if Q in a quantum group can arise as some geometric parameter, that's pretty cool. So we can probably understand much better the structure, or at least ask questions in completely new ways. Similarly, I have to admit I knew nothing about logarithmic VOAs, especially I mentioned 2013. So my knowledge of logarithmic VOAs was literally zero at that point. In fact, even at 2018, when subjects started kind of come out at us from this perspective, I still knew nothing, but in the past 5 years, I had to learn something. And in fact, Terry was my direct or indirect teacher, because first thing I found on the web is a nice set of lectures that he wrote, and that was a great start. So, but by doing this, we don't have to be just users of logarithmic VOAs, which are very cool, interesting, mysterious things on their own right. We can actually contribute to it. And I'll give you an example of such contribution by telling you the following statement. So it predicts how in logarithmic VOAs characters should behave. So I told you that in every such context, that we'll be discussing, there is always a way to reformulate the question in terms of function of Q, that's counting states. For example, in two-dimensional CFT, so first I'll start in usual two-dimensional CFT or usual vertex operator algebra. We have this object chi of Q, which is again some proper trace, or if you got it from elliptic genus, it's super trace with minus signs and so on and so forth. But it is basically sum over an q to the n, maybe plus some fractional power delta, okay? And n's are here integers. So you can ask, how fast are my coefficients growing, okay? What's the rate of growth of an? And it's a basic fact that if you have Q of t in d dimensions or C of t in d dimensions, then do you know how an should grow in general? With n. So if it's larger, then the number of states may be larger. And it also depends on dimension, because if I have high dimensional theory, I have more and more states to worry about. So it's a function that increases both with n and d. Okay, so yeah, this is a cool fact that's actually not usually taught in QFT courses, but it's actually very basic, so it's not super deep. And by the way, defining it in CFT and QFT, there is not much difference because we don't understand even the question unless QFT is at a fixed point, so that's why I use slash. So it goes as n to the d minus 1 over d, okay? So d is a total space-time dimension. That's, for instance, if you work with a 2D theory, where when I say 2D, it means 1 plus 1. So d is equal to 2 in that case. And yeah, so maybe I'll just write and give you a couple of cases. So if d is equal to 2, then this is n to the 1/2. Sorry, I should write log of an. That's the right thing. And this particular rate is actually known as Cardy formula or Cardy growth. So I'll come back to it in a second, but let's do even more basic case. So this is d equals 2. D equals 1 would be the first non-trivial case. That's where we have quantum mechanics, because quantum mechanics is 0 plus 1 dimensional QFT. You don't have space and you only have time in quantum mechanical setup. So this tells you n to the 0. So it means that it roughly doesn't grow. And actually that's true, we just saw it earlier today. The states of harmonic oscillator, there is one an is equal to 1 for every n. So it actually doesn't grow. So that's consistent, right? So this is n to the 0. If you tell me that there are like 5 bosons in your harmonic in your quantum mechanical system, there will be basically some finite or low growth of this states controlled by how many bosonic degrees of freedom you have. And fermionic contribute even less. But then it goes up. For instance, if you're in d equals 3, then this will tell us, d equals 3 means 2/3. So this would be n to the 2/3, okay? So therefore, I should expect that if I'm talking about, say, 3D theories with some supersymmetry and whatnot, and try to count states, just on, again, without knowing more about the system, if it's generic, you would expect that my growth of ANs should be n to the 2/3 in 3 dimensions. But this turns out to be incorrect. So this turns out to be incorrect because we're counting very special states, very nice. So it's true that in my 3D n equals 2 theories that we're talking about, the overall Hilbert space is such that the growth is n to the 2/3. But for this particular BPS states, the growth turns out to be n to the 1/2, exactly as it was in 2 dimensions. So therefore, this, for the purpose of BPS spectra, these three-dimensional theories will behave very much like two-dimensional theories, in fact, very much like two-dimensional CFTs. So in that sense, this is a good thing. 3D guys will be more like 2D CFTs. But they will turn out to be more general than usual 2D unitary CFTs, and that's why we're gonna learn something about log VOA. So let me now erase this and tell you what Mr. Cardy said. So now I'm gonna focus specifically on a two-dimensional case, d equals 2. So we just saw that according to general calculation, we should have log an go as n to the 1/2, but I can restore some of the coefficients here, and that's basically what John Cardy did. First, I'm gonna take log away and push it on the other side, so I'll say that an is exponential, and then for whatever reason I like to write 2 pi here, and then there should be some square root of n. And Cardy basically computed what the rest of the formula is. He said that this should be 1/6 of basic characteristic of a conformal field theory called central charge. More precisely, C effective. So yeah, this fellow is central charge minus 24 times minimal value of the conformal or scaling dimension. I'll call it H, but it actually has same meaning as this delta. I call them different letters for later use. In any case, this shift is maybe not so important, but central charge is a basic characteristic of a CFT. It tells you roughly how many degrees of freedom it is in a CFT. And that's what John Cardy established. So this particular formula. Okay. So now a theorem. So I told you that we can do something new or have a concrete prediction. So based on this this perspective, you can actually prove that. So this is a theorem for 3D theories / conjecture for log VOAs. So maybe I should clarify. It's a horrible thing to say, theorem / conjecture. So it's a theorem for 3D perspective that we'll be using, and a conjecture for log VOAs, because there is an independent conjecture that what I'll tell you has applications to log VOAs. And either way, it's in recent joint work with Mrunmei Jagadale. So this is recent. Oops, not that recent. And as you can see, it's like 10 years after some of these things started to being defined, formed, and so on and so forth. So it's, again, in this first introductory lecture, I'm basically showing you the span of how far we can go, what basic things that we'll be talking about can buy you in the end, and my job is kind of to make this 10-year span of development smoother or more reasonable. And here, analogous statement is the following. So you have the same expression for characters. So chi of q is sum over n a n q to the n. There are various bells and whistles. For instance, I don't know if Terry or I will have will have time to tell you that this should be called quasi-characters, not characters in logarithmic context, and so on. It doesn't really matter. They're analogs of characters. We're trying to do the same thing. We're trying to count states. But one important thing that we surely will tell you, both me and Terry, I'm pretty sure, is that log VOAs are non-unitary. So world of non-unitary VOAs or CFTs is kind of more shaky. That's why when I was a kid, I was told to never learn this subject because it's never going to be found in physics. Oh God, it's completely wrong. So it's being found in so many physical systems, not only supersymmetric ones I'm going to tell you about, but also in questions like percolation, sand pile models, all kinds of cool other applications, interface growth, and so on. And therefore, it is good to study them. So it's actually a pity that log VOAs were kind of excluded from our exclusive club for so many years, because they're very cool systems. In many ways, they're better than the usual CFT. So sometimes relaxing conditions is a good thing. But the fact that we relax something and make them non-unitary will make this central charge a complex number. And one thing that you can observe is that, so the analogous, so the theorem or statement or prediction for this ANs is that it's going to be real part, because these coefficients are still going to be integers. But this C may be now a complex number. And there is another correction to it. So there is this plus 2 pi times some rational number. I'll call it R. So this R is rational number. And what's meaningful, of course, it's a rational number mod integers, because if I change R by integer, nothing changes. And therefore, most kind of, oops, so this should be also here in the exponent. So easier or more meaningful thing is probably exponential of 2 pi I R. And this is point on a unit circle, and that's the point which, in the language of resurgence or saddles, which will make the dominant contribution. So if we get there, I'll explain where it comes from. I'll show you like the arguments and so on. So this is meant to be some point on a unit circle. But I can illustrate for you the effect of it. So I'm still discussing why. I'm still basically now, previous part was what. Now we are still on the why. I'm going to erase this, but I'll show you something else instead. So if I just plot these coefficients, an versus n, then Mr. Cardy would tell you that they should grow pretty fast. It's not polynomial growth. It's also not exponential growth. It's rather growth of e to the square root of n, right? That's what we had. So a picture would be like this. So there are two new things happening in logarithmic world. In logarithmic VOAs or CFTs, what this predicts, and again, that's a prediction. It hasn't really been checked on that many VOAs, because first of all, we don't have that many VOAs. That's going to be another benefit. We'll construct for you lots of new examples. But among other things, what it predicts is two things. So first of all, it predicts that things oscillate. So they grow in absolute value. I'm poor at drawing it, but you should imagine that absolute value growth as exponential of square root of n, that's as Cardy predicted, but there is also oscillation. And more importantly, this rational number R, its denominator will tell you how many different curves like this you see. For example, if R is 7 over 5, then, or 5 over 7, then you'll see either 5 or 7 of these curves branches. I'll try to draw them with different colors. So for instance, you may see something like, I don't know, something like this. So you'll see if you just plot the coefficients an in a character or quasi-character of log VOA, you're not going to see one nice curve, which is what you typically see in the usual CFT. You'll see some number of them, and that number is exactly the denominator of that rational number R. Okay? So that's a very concrete prediction. That's a very concrete theorem or outcome of the story, which was not known before. It's actually hard to get to this directly from VOA or CFT perspectives. I wish I knew how to prove it just using log VOA techniques, but this is something that this new perspective buys for us. So that's an example. Again, this is answering question why we're doing it. So what does it gain for us? Okay. Any questions? Um, well, Cardi showed his result assuming modularity. So by now there are several ways to prove it actually. Simplest one, and probably the one which is used most of the time in textbooks, is to use properties of characters um, that refer to some kind of SL2Z behavior. So here, the issue with log VOAs is that we don't have that. So we don't, and that's actually very cutting edge research to understand what is the analog of modular transforms for characters. That's why people introduce this notion of quasi-characters and so on. So unfortunately, we don't have that technique. Right. Maybe, yeah, sorry, what was your question? How, in what sense you see explicitly? Oh, 2 by 3 is, so they're separate computations. So 2 by 3 is general consideration in QFT or CFT. So that's actually, I would say, easier, definitely conceptually easier. And this square root n to the 1/2 in CFT can be shown by those general considerations as well as modularity. So that's what I was referring to in 2 dimensions. Modularity is more specific to that. So this, again, I'll show you the proof of this theorem or the argument if there is time. It will use very 3-dimensional techniques. And then there is additional conjecture, sometimes called 3D modularity conjecture, that whatever we, I mean, the construct, this BPS spectrum in 3 dimensions is realizing spectrum of log VOA. So that's going to be a separate sort of additional thing. So therefore, in that sense, it will be theorem and a conjecture. So there is something to prove, but there is also unknown. And again, I don't know derivation of this directly in log CFTs. So therefore, to answer your question, there are several levels. One is simplest, I would say it's kind of homework actually, to try to work out this formula n to the d minus 1 over d in d dimension. That's a good exercise. So that will also give you 1/2 in dimension 2, but you can gain more information, namely precise coefficients and so on. That's what Cardi did. We will get all this 1/6 and so on if we use modular properties. So, but the first, this n to the d minus 1 over d is a good homework exercise. Yeah. And basically it says that QFT, that's another useful perspective, is I mean, QFT literally is a bunch of harmonic oscillators. Because if we have some description of QFT in terms of Lagrangian, sometimes we don't, but if we do, then it's very clear because our fields are, we usually write them as modes, we have creation and annihilation operators, and we basically have a bunch of harmonic oscillators. So basically this formula tells you how many harmonic oscillators you need in d dimensions to describe an actual QFT. That's another way to interpret this formula. I hope I at least partially answered your question. We can, of course, discuss further. Okay, so far so good. Everything is clear. Any other questions? In fact, let me give you an example or homework. So I promised problems and homeworks, like research problems and simpler homeworks. So pretend that we'll be talking about Q series. So pretend that your Q series is of the following form. I believe it's this one. So first, yeah, where is it? Yeah, I think so. 2 in the numerator. Okay, very good. Right. So what's written here. So I introduced yet another notion here, this object, which is a parenthesis with two variables, x and q, and some kind of infinity. How many of you know what this means? Please raise your hand. Okay, pretty much everybody. So you didn't raise your hand. There is this nice cartoon, Madagascar, and then there is in when the animals get to this island, there is a moment where like, Maurice, you didn't raise your hand, so your comments will be struck out of the lot. Anyway, so what this is by definition, many of you already know. So this is k growing from 0 to infinity, product 1 minus x q to the k. Well, maybe let me use j. I don't know, doesn't really matter. So it's an infinite product. So that's what this infinity means. This is called Kupa-Heimer. It's a very simple thing. You can code it in Mathematica in one line. It's Mathematica already knows Heimer. Even if it didn't, you can easily just do product up to, I don't know, j equals 100, and write this as we did. So here notice I substitute for x specific powers of q, for example, 2, 3, and q, and so on. And you just write it as expansion of the type we had before, from 0 to infinity, an q to the n plus some maybe fractional part delta. And you ask yourself how fast an's grow. So this is a good example of BPS state counting in a 3D theory. I'm not going to tell you which one it is. So in fact, I can try to ask show of hands who can guess what this theory is. Well, maybe I'll reveal the answer. It's actually not, I don't see why I should keep it a secret. It's a very simple theory. It's a 3D n equals 2 theory with a single field phi, which is so-called chiral superfield, and then 3D n equals 2 language, and superpotential phi cubed. So in other words, this is basically 3D n equals 2 Ising model, okay? It's, so just like two-dimensional usual Ising model can be realized as Landau-Ginzburg model, this is basically a 3D version of that, or supersymmetric version. So this is 3D n equals 2 Ising model. The simplest theory. So in any case, all this doesn't matter. I got it from somewhere, or maybe I just dreamt it up. Just as a homework, compute ants and how fast they grow. I mean, check what is the C effective and check what is the value of R. That's a fun calculation. So just to have something concrete. Okay. So I'm still in the why question. I'm still trying to outline in this introductory lecture now what and why. And again, what I already promised you that we're not going to venture outside of that world that we outlined, but we're still in the why. And there is another why. So just like studying this combined systems leads you to insights into something you didn't expect. I was completely honest when I said 5 years ago I had no idea what log VOAs are, and I had to learn them from scratch. But they also give us insights in the world of something that we did expect. For instance, studying this manifolds of different dimension. So if you study MD, and this is your D, then it does provide insight into invariants. And our understanding, so this is roughly complexity in a sense of how rich or interesting the structure of smooth d-dimensional manifolds is, varies with D. So D could be, I don't know, 0, 1, 2, 3, 4, 5, 6, and so on. 7. So for instance, if D is equal to 7, then Milner taught us that there are 28 7-dimensional spheres, so that's a pretty cool subject. There is something, I mean, I should put a point above 0 because complexity, or I mean, the structure is rich and interesting. On the other side, if we start with 0, we're studying points. Okay, so there is not much study. I should probably start at the origin. One-dimensional manifolds, well, if closed ones, they're just circles or pieces of line segments. So, I mean, it's probably somewhere here, just above ground energy. In 2 dimensions, smooth 2-dimensional manifolds, classified by genus, maybe marked points. So again, it's pretty boring. In 3 dimensions, story gets very rich and interesting. And well, fairly recently, by math standards, Perelman proved that they behave the way we expect them to behave. So you can see what's happening. So this sort of picture looks kind of like this, and it definitely has a peak and dimension 4. Okay, so motivation for studying d-dimensional manifolds is, or for me to work on this 3D correspondence or its application to 4 manifolds, because here we do need a lot of new invariants because we don't understand 4 manifolds, smooth 4 manifolds. Our understanding currently is very, very poor. So just to give you a simple example, in the context of 3-dimensional topology where Perelman proved what we expected, everybody knew what the result had to be for many, many decades. There was no doubt about it. I mean, it was just a matter of finding the right way to prove it. In context of dimension 4, we actually don't know if smooth Poincare conjecture is true or false. If you ask experts, the opinions will be completely split, and it's very hard to guess because it will be really a random guess. We're way too far from understanding the theory to even have an educated guess. So that's what this picture illustrates. Now, I'm going to replace MD. A similar thing is true about QFT. So if you ask about QFT in d dimensions, so I can keep the horizontal axis, you'll see a somewhat similar picture because in dimension 0, it's like a matrix model. This is something very integrable, very solvable. So Lotta's advisor made a great contribution to this subject as well as many other people. In dimension 1, this is quantum mechanics. Again, this is slightly better, but well, it's not as mysterious as QFT. In 2 dimensions, it gets a little bit more interesting, maybe kind of goes slightly up. But for instance, you still don't have non-trivial gauge dynamics because gauge fields have no propagating degrees of freedom in 2 dimensions. You probably know this fact from your QED course, which says that in 4 dimensions, photons have 2 polarizations. So 4 minus 2 is 2. That's where this number comes from. In general, for gauge fields in d dimensions, the number of degrees of freedom is d minus 2. So if you're in d equals 2, there are no physical kind of degrees of freedom. So you cannot have really a QED or QCD in 2 dimensions. It basically imposes just charge conservation. So it should be actually quite simple. But in 3 dimensions, it already starts getting pretty interesting. And if I go beyond this, on kind of change gears, go to the other side of this diagram, we believe that beyond 6 dimensions, there are no interesting non-gravitational interacting QFTs. So basically, this is like empty, okay? This part of the diagram is absent. So I told you that in 6D02 theories, they're fairly well classified, so they're very well structured. So there is something, well, maybe I shouldn't put it at 0, but there is a point somewhere here. And it's a non-trivial question how many 6D theories we have because we're kind of right at the edge and things are pretty constrained. So definitely world of 5 theories is much richer, so I should probably put a point higher. And you can see what's happening. Same picture emerges that things that if you approach it from 2 sides, we have either simplicity imposed due to low dimension or too many constraints imposed by high dimensions. And optimal spawn is somewhere in the middle where 4D QFTs is again something we don't understand. For example, we have no idea how to define it non-perturbatively and so on. So picture looks kind of like this. So it's very easy to remember. If you're a mathematician, think about this diagram representing complexity of manifolds, smooth manifolds. If you're a physicist, think about diagram representing complexity of QFTs. So therefore, now I come to a more serious point that I was trying to illustrate with this sort of why statements. That by playing with the systems, we're going to learn something about non-perturbative physics and strongly coupled so if you're a physicist, then physics of strongly coupled systems QFTs is what may be of interest to you. In particular, in general, we know how to define QFT perturbatively at the physics level of rigor. Of course, all disclaimers for math part of the audience. So thanks to Mr. Feynman and others. But we have no non-perturbative definition of QFTD in dimension greater than 2. In dimension 2, you can kind of cheat. Again, in dimension less than 2, there is no QFT, just quantum mechanics. In dimension 2, you can cheat because thanks to Borchards and others, we have mathematical definition of vertex algebra, so we can say at least what the fixed point is. So we can define CFTs or fixed points as built out of left and right vertex operator algebras. That's algebraic language. If you like language of SLEs, stochastic linear equations, that's yet another mathematical way to do it. But both are extremely special to dimension 2. In dimension greater than 2, we have no mathematical tools at all. And that's for perturbative QFT. But non-perturbatively, even physicists have no idea what to do in general. And part of the reason is that we don't know how to handle strongly coupled systems. Systems where you don't have a dial that you can tune to small values, and that's going to be your perturbative coupling constant, but systems which are intrinsically strongly coupled in quantum, such as, again, quantum phase transition, for instance. So this is something that's going to be very useful. In particular, we'll see many examples of such strongly coupled systems emerging from what I raised from this 2D theories labeled by 4 manifolds. They're usually called T of M4. And similarly, 3-dimensional theories associated to 3 manifolds called T of M3 will provide us lots of examples. So examples. So generic theories of this type, even up to present day, have no Lagrangian description. So that's a cool thing. I mean, that's why studying them is hard, or somewhat hard, because there is no Lagrangian to write. You cannot just say, oh, I'm going to apply my Feynman rules to this and that. There is nothing to apply to. I mean, if there is no Lagrangian, how do you even start, right? So that basically forces you to think about how to define QFTs in ways that doesn't use Lagrangian. QFTs that don't use perturbative couplings. So many of our examples, not all, but many, again, generically, will be examples where no Lagrangian description is known. I should maybe emphasize is known because it doesn't prevent you guys or future generation from discovering how to write the Lagrangian. So it may exist. I wouldn't be terribly surprised because we're talking about QFTs in fairly low dimensions. So from 4 manifolds, we'll be in dimension 2. Notice that this is fairly low point on this diagram. In dimension 3, it's a little higher, but still it's not like all the way to dimension 4. So in some sense, we'll be trading complexity of 3 manifolds and 4 manifolds for what one could argue lower level of complexity in QFT. So it's actually good that QFT is fairly low dimensional. So we'll be able to get some mileage. And even here, we'll have no Lagrangian description. Yeah. That's a very good question, and that's exactly what we're going to do. So the rest of my lectures will be precisely to write you a Q-series which encodes BPS spectrum of this series. I'm not going to say anything about non-BPS states, so I have no idea what they are, actually. But magically, and that's actually should be really viewed as magic at this point, besides the fact that I have no idea what Lagrangian is, we'll be able to write their BPS spectrum. So unfortunately, it's not good enough, at least I'm not good enough to reproduce theory from just knowing its BPS spectrum. And the map is probably highly non-unique, so we still have a lot of work to do. But it's actually quite cool that despite all of this, we'll be able to say something. And basically, your question is very much in line with my point here that we'll see tools that will allow us to say something about the theory. It's not everything, it's something. Um, well, if you ask, right, for instance, if I didn't tell you that this thing comes from some particular theory, the best you can do is probably check how fast ANs grow. And if they grow, say, as exponential of n squared, then I know for a fact that it does not come from any quasi-local QFT, right? Because that would be against any growth that we saw. So there are simple criteria like this. If it does satisfy criteria, then it's a non-trivial question. So it's like a math question, uniqueness. So can you find a theory such that its spectrum matches whatever we're going to propose? I don't know. In general, if you give me like random Q series, and if it does exist, at least my bet will be that it's highly non-unique. Why? Because we're talking about BPS spectrum, so I can add to it something non-BPS, and I mean, to my theory, I'm probably not going to change. So I suspect the answer is generically highly non-unique, but existence is slightly non-trivial. In our case, the logic, luckily we don't need to face this question, because here the logic will be that we'll actually construct some description of these theories. It's not going to be enough to fully describe them, but we'll construct something, and then that something will be enough to compute this BPS partition function. So in some sense, it will be very structured. We'll start with theory or manifold, and construct for you this Q series that counts whatever it counts. So therefore, question does not arise. You can, I mean, it's only one directional, but reverse is highly non-trivial. Yeah. Yeah, very good. Unfortunately, or fortunately for me, that's actually exciting part. That's something I should have mentioned. My 6D starting point is already non-Lagrangian. So that's the cool thing. If my 6D point is Lagrangian, I would consider that to some extent boring, to be honest, by reasons I'll explain in the rest of the lectures, both for four manifold invariants and other things. But coolest thing is when you have no Lagrangian in either UV or IR across the dimensions, ever. So that's in some sense exciting point. So the starting point, that's why I'm going to use 0, 2 most of the time. These theories have no Lagrangian description, and the endpoint will have no Lagrangian description. So that's why we can hope to get something new. In part because after 20 or so or 30 years of experience, Lagrangian theories, we know that they don't produce new invariants of four manifolds. It's almost a theorem now that everything boils down to Seiberg-Witten invariants, which capture very little of topology, only when you have non-trivial Betti number. So in particular, they say absolutely nothing about homology spheres. And that's why actually it's good to avoid Lagrangian description. If you have Lagrangian description for purposes that I highlighted as like benefits of this, it's actually going to be bad. So. Okay. So I have a couple more minutes, so maybe I'll say the following. So there are two things I need to add to this introductory part, and one I'll save for a second lecture. It will be fairly quick. I'll tell you another thing. It's not like what do we gain. There were several puzzles which were actually leading to these developments in 2013. Puzzles, meaning big puzzles in the community that we didn't know how to solve, and they were really baffling. So I'll tell you about that in the second lecture. But in the meantime, maybe let me illustrate where some of these combined 2D, 3D systems come from, and at least so that you see one natural origin for them, and then I'll use it in the future lectures. So suppose your starting point is 6-dimensional. So that's going to be a maximal dimension, will never exceed that, and so on. And you want to consider some 6D theory, could be 0, 2 or 0, 1 on 4 manifold, okay? So the way mathematicians build manifolds, in fact, in any dimension, is by cutting and gluing. So they chop them in basic pieces, they classify basic pieces, and then once you know how to glue pieces together, you got yourself a Lego type game where you can assemble pieces and produce anything you want. So the reason Lego is so popular because out of elementary pieces, you can build so many cool toys, right? I mean, variety of toy skyscrapers, cars, airplanes, houses, animals, and so on and so forth. But pieces are very basic, right? They're just tiny Lego blocks. So same thing here. The logic is break your manifold or any dimension into basic elementary pieces and glue them together. So if you start with a 4 manifold and try to chop it, you necessarily create 3-dimensional boundaries, simply because a boundary of D manifold is D minus 1 dimensional. So therefore, a boundary of M4 will have to be M3, some 3 manifold. And here I'm going to illustrate the following thing. Suppose you cut it along M3, and since we're going to be trying to work with these manifolds topologically, so namely the 6-dimensional theory will be partially topologically twisted along 3 manifolds or 4 manifolds, this will allow us to do any continuous deformations to the metric. In particular, I'm allowed to stretch my region in this 4 manifold near the cut. So it will produce this sort of neck, long neck, where geometry will look like, in this neck, it will be M3 cross interval, right? Now, let's think about this configuration for a second. Suppose I don't have this ears or caps on the left and the right, and all I have is this region in the middle, and here in the middle, it looks like I'm compactifying my 6D theory on a 3 manifold. So what I should get upon this compactification is 3D n equals 2 theory T of M3 that we associate to 3 manifold that sits in the cut, right? And in fact, this theory lives on the interval. So if I want, I can even illustrate it by drawing this interval. So this is going to be like 3-dimensional world after compactification. And this direction, we can call it x3, for instance, using some of the coordinates, is going to be exactly this direction, x3. But then if I continue, so I am someone who lives in this 3D n equals 2 theory. So there is a person here. Let's say this is me. Okay. I try to walk far to the left in this x3 direction, and I see that I cannot go because in dimensions that are hidden from me, so physicists would call them hidden dimensions, the world actually ends. My manifold stops. So I have to have, so this, I mean, I could use this picture of a cylinder all the way, but not far to the left where I'm getting capped off. And here the four-dimensional nature of the problem kicks in. So I use all four dimensions, not just three. So in particular, I break more supersymmetry, and the world stops, and supersymmetry is less, so I end up with a 2D 0-2 boundary condition. So it's a boundary condition that I can, if this is M4 minus, I can say that this is T of M4 minus 0-2 boundary condition. So if I walk all the way here, same thing happens on the right. If this is M4 plus, then I get two-dimensional 0-2 boundary condition T of M4 plus. And this is how I build my four manifold, or mathematicians build four manifold out of pieces M4 minus and M4 plus, which they take a union over three-dimensional boundary that's common to both pieces, okay? So therefore, if you think about, again, without knowing too many details about the 6D theories, how they're compactified and so on, which is actually, like I told you, we don't have Lagrangian description for them, so we don't know much anyway. But just from simple dimension counting, the fact that our dimensions always have to add up to 6, you can deduce this picture. Because here, 3 plus 3 is 6, and here, 4 plus 2 is 6. So therefore, that's how you would arrive to this 2D, 3D combined systems, where you have, say, 3D n equals 2 theory with 2D 0-2 boundaries. And that was actually originally how things were discovered. But I'll tell you several other perspectives in the second lecture. So I think I'm out of time. We can go enjoy a coffee break. Feel free to ask me more questions during coffee and also during next lectures.